Hello, welcome to your third lesson on the binomial theorem. In this one, we are assuming a kind of mastery of the theorem, and we're going to try some varied problems together. Let's get rolling. Okay, to warm up, I have this problem for you here. So, in the expansion of a minus b squared to the sixth power, what is the coefficient of the term in a cubed b6? So imagine this is expanded. One of the terms has that in it. What is the coefficient? Okay, let's begin here, where we often begin. Here's going to be our first term, here's our second part of the binomial, and then our combination. Tell me what numbers should go here, 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 and here. So tell me the four numbers, the 2 for the combination and 2 for the exponents. Okay, hope you came up with 3, 3, and then 6, choose 3. Reason is we know the term has to have a cubed, so we know that a must have a third power on it. And that means this must be a third power to make these combine to 6, and that seems to work out here because b squared to the third power here is b to 6. Great, so we know it's that, and then 6 choose 3. Now expand that fully and find out what the coefficient is. Okay, check your work here. Coefficient is negative 20. Hope you got that. Next one in our warm-up. So these are the easier problems, right? Here is, we're looking for the fourth term in the expansion of 2x minus k to the 8th power. And we're told the fourth term equals this. So find the value of k. So let's begin here again as well, right? Here's our first part of the binomial. Here's our second. Tell me again, what should the numbers be here, 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 and here? Okay, so we were told this is the fourth term. And in the fourth term, we always know the exponent on the b thing, on the second thing in our binomial, the k in this case. The exponent on that always has to be 1 less than the term number. So fourth term means this is 3. Then we need a 5 here to make 8. And then we have 8 choose 3. Great. Take that, expand this, and then set it equal to this, because we know the fourth term is this. And that will allow you to solve for k. Try it out. Okay, so again, we know that equals this, because we're told the fourth term is that. Okay, now expanding this side becomes all this, and solving, we get k equals 6. So check your work carefully, and I hope it worked out for you. Okay, now I'm going to do a little reteach moment. We ended off in our recent lesson at this place in the binomial theorem. So we're going to show you the problem we left off on. This problem here, we have a more complicated binomial here to the 6th power, and we're looking for the constant term. Constant term, again, means the term with no variable in it. So when this expands, it becomes a string of many terms, and in this case, this is a 6th power. So when this expands, it will be 7 terms, but only one of those terms will have no variable in it. So we're looking for the term that has x to 0 power, which means 1. There's no x. So let's set up again. Here's our first thing. Here's our second thing. And notice I brought that x up to make it x to the negative 1. Okay, so now the exponents are r, because for now we're going to say we have an unknown. We don't know what term number it is. We just know we need x to 0 to be the result of all the x's. So some power here, we don't know what power. Therefore, this one is 6 minus r. Because let's say this was a 4, we would know that's 2 over here, because they always have to add up that number. So 6 minus r is that power. And then our combination, we always do the 6, choose the b thing exponent. So 6 choose r. Great, there's that. Expanding that, well, first of all, we know that we're looking for the constant term. So we're looking for when all the parts in here that are the variable x have to become x to 0. So I'm going to ignore all the numbers, so this is going to create some number, ignore that. 2 to the 6 minus r power, some number, ignore that. I only want the things with the variable. So here, x squared, and when you have an exponent here, you multiply. So 2 times 6 times that is 12 minus 2r, because you multiply the 6 and the minus r. And then over here, I'm going to ignore the 3 and just focus on the variable again. So x to minus 1r here, you multiply negative r. So again, I've just looked at x here because we know the x thing must be x to 0 in the constant term, ignoring all the numbers. Now combine these. When you multiply, you add exponents. So what is that? Combine there, 12 minus 3r. And we know now that x to 0 must equal this. Now we have x to some power, x to some other power. Those powers must be equal if this is really an equation. So 0 equals that. Solve for r. That tells us the exponent must be 4 here. So now we can write this. We know this is now 4. So this is 6 minus 4, which is 2. That makes sense. They make 6 together. And then 6 choose 4. Great. Expand that fully. Let's check our work. Expanding it. There we go. notice the x's cancel, as they should. We were looking for the constant term, so notice here, we found the only exponents in our expansion that would create x values that cancel. Look, 2 times 2, x to the fourth, 4 times negative 1, x to the negative 4. Those will cancel. When you multiply those two, they cancel, x to 0. Great. Let's look at one more like that. So now, this is our first new problem here. You haven't seen one quite like this yet, but we have this one here. So again, kind of a tough binomial to 11th power, and we're looking for the term in x to the 9th power. So instead of now the constant term, we're looking for when does this produce a term where x is to the 9th power. So use the same approach by doing the r and the 11 minus r and all that. Do that, and let's see if you can find a value for r first. What exponent should go on the b term to create the situation we need? So begin like this. Again, we say this is to the r, this thing here, which is this, right? Negative 3, and then x went up to become x to the negative 1 power. And that is to some unknown power. And this will then be 11 minus r. Over here, then, we have 11, choose r. Now, again, our goal here is not the constant term. It is the term with x to the 9th in it. So just like the last one, but now instead of x to 0 equals the x things, we need x to the 9th equals whatever the x things are here. So let's try. So we need the result of x to the 9th, and the only things with x here are x cubed, so that multiplied is x 33 minus 3r when you multiply those. And over here, x to the negative 1 with the r here is x to the negative r. Ignoring all the numbers, so we're ignoring the combination, we're ignoring the negative 3, we're just looking at the variables because we know we want the term with the variable being this. Okay, combine these. When you multiply, you add here, so we get 33 minus 4r. Now solve the exponents by saying them equal to each other, and you get r equals 6. Great. So now we know this must be 6, therefore this must be 5, and therefore this is 11, choose 6. Take this now all the way and see what happens. Do you end up with a term that has x to the 9th? Well, you should. Okay, let's check our work. This becomes 15, this becomes negative 6, and, well, yeah, combine the x15, x to the negative 6. When you add those exponents, it's 9. And that's what we wanted, the term where x is 9. Everything else multiplied becomes this. Great, hope that one worked out. Let's keep going. Here's another one, slightly more challenging. Similar kind of problem, but more challenging. Here's a complex binomial, and it also has a multiplier in front of it. So we've looked at one like this in class as well. So consider the expansion of this, and then every term that this produces will then also be multiplied by x to the 7th. So that's part of the process here. And we know the constant term, again, is 168 here. The constant term is 168. So see if you can find k, see if you can set it up. Let's begin like this again. So this, again, expands into, since this is a 7, this will expand into 8 different terms, and this is going to be one of those terms. And each of those 8 terms will then be multiplied by x to the 7th. So whatever term I'm looking for here is multiplied by x to the 7th, because all the terms this produces will be multiplied by that. Now, what do we know? What numbers should these be again? So what numbers should be here, 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 and here? Well, it's not really numbers, right? Because again, we have an unknown. We don't know what term, but we know some power on this, r, and over here, 7 minus r because of that. And over here, then, we have 7, choose r. So same process as before, but now we have this extra bit in front because every term is multiplied by that. So let's take this further now, and let's see if you can solve for r. And again, we're looking for the constant term, so x to the 0 power, right? Let's try. Okay, here's x to the 0 power. Here, this then, when I'm looking just at the x portions, right? Because now we're going to ignore the numbers. So I'm going to ignore the combination. I'm going to ignore that 2 on the bottom there. I'm going to ignore the k here as well, because that represents some number. And I'm just going to focus on the x. So this here and this here. This, when you multiply by this exponent, multiply exponents when there's parentheses, that becomes 28 minus 4r here. And over here, we have x in the denominator. So if I bring it up, it's x to the negative 3 power. And then that times r is this, negative 3r. So now I have all the x portions, including that one, the multiplier in front, ignoring the numbers, and it must be x to the 0. So now we're going to combine these exponents using our laws of exponents. We have multiplication, so we're going to add all those. And we have 35 when you add 28 and 7. You have negative 4r, negative 3r is negative 7r. And now make your equation. The exponents must be equal to one another, and that means r is equal to 5. All right, so now that we know that r is equal to 5, we can fill in our portions of our term here. Here's 5, here's 2, here's 7, choose 5. Now the next step, you could of course expand all that, include all the x's and all that, but we know again that these x's will cancel. So, right, look, x to the 4th, and there's a 2 here, so that becomes x to the 8th, and there's an x to the 7th, so x to the 7th, x to the 8th combined is x to the 15th, and over here we have x to the 15th on the bottom in the denominator. So the x's will cancel. So when we go on to the next step, we don't have to worry about the x's. We already know they will cancel because we already set it up to be the constant term. So ignore the x's and just apply just the numerical parts and set them equal to 168. So check it out like this. Here's the numerical parts. The combination is one part of the coefficient. And then over here, if we ignore the x, because we know it's going to cancel away in a moment, we just have a half left. And a half to the second powers is going to be 1/4 in just a moment. Over here, k is our only number, because again, we're ignoring the x. We know it's going to cancel in a moment. So we have k to the 5th. And all of that produces the constant term, which is basically the coefficient. The x's are gone, right? So we have that equals to that. So now, solving this for k. So this becomes 21, the combination. Here's 1/4, k to the 5th. Now I'm going to multiply by 4 over here and divide by 21. So there's k to the 5th equals 32. And k equals 2. A little bit tougher. These are definitely tougher, but I hope you're putting the pieces together and the logic behind it is starting to make more and more sense the more you see. Let's keep going. So here is another one. Okay, let's see if we can do this one. A little bit tougher, I think. We have in part A here, we're going to expand this. So expand this fully. That means if you see a 5 here, it's going to be 6 terms. Okay, let's check our expansion first. So that's what this thing expanded fully should look like. Now, let's take a look at question B. It looks a little strange at first, but let me explain it and see if you can come up with it. Basically, we're looking for the term in x to the 4th power in this, I guess, expression here, right? Notice that expression for the second half of it is the same binomial we had here, x minus 5 to the 5th power. So that means to solve this, if you were to expand this whole thing here, first you would expand that using our binomial theorem, and then multiply everything by 2x minus 1. So it becomes something here. Basically, you are doing 2x minus 1 times all of this, right? It's 2x minus 1 times that expansion. So if you're doing 2x minus 1 times this, that means every term in here is going to be multiplied by 2x minus 1. It's just like the questions we had before when you had just like x to some power in front of our binomial. Now we have 2x minus 1 in front of it. But it's the same idea. 2x minus 1 will multiply everything here. And if it's multiplying everything here, imagine each of these terms, the x portion of it is going to be multiplied by 2x at some point. So each of these will be multiplied by 2x. So now to answer this question, which of these, when multiplied by that 2x, will create x to the 4th, right? Because that's the term we're looking for. So decide which of these terms will become x to the 4th, and then what does that term look like? Okay, so the term containing x to the 4th will be this one right here, because we have x to the 3rd power, and when you multiply that by 2x, it will become x to the 4th. So there's that. Of course, if you multiply by 2x minus 1, you're also going to multiply that by negative 1, but then it'll just remain x to the 3rd power, and that's part of another term. This is the only part that gives us that x to the 4th right there. All right, here is an exam-style question. These are definitely now our final step in terms of challenge. If you've been doing okay so far, great. You're nearly at that very top level of problem, and now we've arrived at the ones I think are the toughest for a lot of students. So look at this. We have, in the expansion of this to some nth power there, the coefficient of x cubed is 2 times the coefficient of the x squared term. So this will produce a bunch of terms. We don't know how many because this is n. But there will be an x cubed term and there will be another one with x squared. And we know the coefficient of this one is twice the coefficient of this one. Interesting. How do you even approach this? Let's take a look. Let's set up first our binomial term for the one that has x cubed in it. So what will that look like? What do we do to x here? What are the 4 numbers? Here, 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 here. Okay, the numbers are 3, n minus 3, and then n and n minus 3 here. Why? Let's take a look. First of all, we know we're creating the term with x cubed in it. So we know that's only created if that thing is to the 3rd power. Okay, so that means the 1 must be to whatever remaining number, right? If this was a 10, for example, we would do 10 minus 3 and we'd say this is 7. because they have to make 10. But in this case, we don't know what that is, so we put n minus 3. It's n minus that. Okay, so you might be feeling it. We're definitely in that realm of challenge problems, are we not? All right, so let's get back into this one we're looking at. So here we set this up already. We said this has to be set up like this, right? So we know this is a 3 because of the x cubed, and then we have this here and this here. Okay, now let's do the same thing for the other term, because it says there's another term with x squared in it. Okay, so set it up. What goes here, 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 and here? Okay, in this case, we know this is the x squared term, so I'm going to put a 2 here. This is n minus 2, because it's that power minus 2. And over here, we have n choose n minus 2. Okay, and we know there's a relationship between that term and that term. It says the coefficients of those terms, the coefficient of this term is 2 times the coefficient of this term. So what is the coefficient of this one, and what is the coefficient of this one? And write an equation for the two, okay? So first of all, all right, what did I do here? Wow, okay, the coefficient of this one. This is where this one gets a little tricky, okay? So when you look at this, if you multiplied everything out there, if you knew what n was, the coefficient would come from the combination, it would come from this number. This x is not part of the coefficient, that's the variable portion, right? So we can ignore that part, and we just need this and this. But 1 to any power, it doesn't matter what power this is, there's always going to be 1, right? 1 to any power is 1. So I'm kind of ignoring that as well. So in the end, the coefficient of this term is going to be composed just of the combination. So that's what I'm doing here. This is the combination, and here's how it works. We know combination formula tells us we do this thing, n factorial, that number on top. So n factorial, we don't know what n is, but if you had a number, it's that number times 1 less than that number times 2 less than that original number times 3 less, right? So we write it like this, dot, dot, dot. Okay, on the bottom, remember, it's n minus 3 factorial, okay? So n minus 3, and then 1 smaller than that, which is n minus 4, dot, dot, dot. And also on the bottom, you have to take these two numbers and subtract them, right? In the combinations formula, we do that thing factorial on top, this thing factorial on the bottom, and on the bottom we also have this minus this factorial. And n minus 3, imagine n minus n cancels the n, and then n minus negative 3 makes it plus 3. So we also have 3 factorial on the bottom. All right, think back to the combinations formula. Now, see if you can set that up for this term as well. Okay, same as we had here. We have only the combination bit because 1 to that power is just 1. We ignore the x because we're just looking at the coefficients. And I set up like this. Here's the n factorial on top. Here's n minus 2 factorial on the bottom. And then times also 2 factorial because n minus 2 is 2. This one also has a 2 in front because I'm writing an equation here that expresses the sentence we had here, which was the coefficient of the x cubed term is 2 times the coefficient of the x squared term. So this is tough stuff, but this is definitely that highest level of these problems. And if you're still with me, fantastic. Keep that brain going. All right, so now what happens? We know if we have a factorial on top and bottom, we can cancel some. We know if we have factorials on top and bottom, we can cancel things. And it's the same principle here, even though we don't know what those numbers are. I see these, they go in n minus 3, next will be n minus 4, so we can actually cancel n minus 3 here, and then the n minus 4 will cancel with the next one here, which is also n minus 4, and so on and so on, right? Those cancel. All the ones to the end cancel, and we're left with just that and that. Over here, some things cancel as well. That cancels, the n minus 3 will cancel the next one there, and on, and all we'll be left with is this here. So we really have this equation now. Those 3 things over 6, because 3 factorial 6 equals 2n, because I multiply that 2 there, and then n minus 1, and on the bottom just a 2. This equation can now be solved. So try it out. What can you do? Can you see anything else that cancels here? I see n times n minus 1 over here, and also here. So you can just cancel those. So now, if I cancel n and n minus 1 here and here, I'm left with just n minus 2 here over 6, and over here, just 2 over 2, which is 1. Solve this for n, we have 8. Okay, definitely tough, but I hope it makes sense. Let's try one more, sort of like that. Similar problem. Now try this one completely on your own. Let's see if you can do it. Find the value of n. Let's check the work. Same process. I'll quickly go through it. You should be checking how you did. This one's tougher, and I'll share a couple of things here. N equals 7, by the way. If you got that, amazing. That's incredible work. Here's the first one. the x cubed term. Here's the x to the fourth term. Here's all that set up like we did before. But there's something extra here. It is this. In the last question, the second part of the binomial was a 1. Here it's a 2. So we can't ignore it like we did in the last question. 2 to some power, it matters. That number is still part of your coefficient. So I kept the 2 to the n minus 3 power here, and I kept a 2 to the n minus 4 power here. Okay, this makes it a little more complicated, but the other principles are the same. Here you look for things to cancel. Here's n minus 3, n minus 4, and that's what will cancel with the ones that follow here. So if that n minus 3, n minus 4, and all those canceled with all the following ones here, all we have is this on top. 6 on the bottom for that, and there's this. On this side, n minus 4, n minus 5, on and on, it would cancel with all the ones here also. So imagine all the 4, 5, all those cancel, but you're left with n, n minus 1, n minus 2, and n minus 3 we also need here, because that one did not cancel. Okay, so there's that. 4 factorial is 24. We have that 2 in front here because it's that value of that term coefficient is twice the other one, just like we had before. Okay, now there's more going on here. So this, I put into this. These ones here, again, I looked at for common things, n, n minus 1, n minus 2, and here it's the same 3. We can cancel them here, and then I put that 2n minus 3 on top. With the 6 over here, they're gone. We have n minus 3, 2. It's a bunch of algebra, and it's not easy, but here we are. When you get to here, I did what's called cross-multiplying, 6 times that, this times this. Canceling some things. 2, this is important. We have this, and we have this here. I got rid of that 2 to some exponent on both sides by dividing by this one over here. If I divide by 2 to the power n minus 3 on both sides, it cancels away, and it's just a 2 that's left over here. Actually, sorry, I divided by 2 to the n minus 4 over here and over here. And when you divide this by 2 to the power n minus 4, you will subtract the exponents, and you just left with 1. So that's why I have a 2 here. It's 2 to the 1. Not easy. Not easy. Hope you're still trying your very best. There's a few more to go. Here is one. Give this one a try. Let's see if you can come up with this using a similar process as we did in the last one. Okay, the term with x cubed looks like this. We need that to be that. We need this to be n minus 3, and then this is n choose n minus 3. Because we're looking for that term, and we know the coefficient is 80 of that one. So let's set up this term here. Okay, n factorial, n minus 3 factorial, 3 factorial, times this. That's the 2x cubed to the third power there. And we know that coefficient, again, the 1 disappears, because 1 to any power is 1. And we know the coefficient of this will be 80, but I'm putting 80x cubed here because I kept the x cubed here, so I need it here. But we can cancel the x cubes right away, and then we'll have just the coefficients, right, equals 80. So solving that, imagine that without the x cubes, then dividing by 8 to get this 10. Solve this out the way we did in recent problems. Try it out. Okay, that expands to this expands to this, cancel the n minus 3 and onwards. Cancel, cancel, cancel all those. You're left with this. Multiply by 6. We got this. Oh, this one's a little different because now we have a quadratic. That's why I made this one follow up the recent ones. It's a quadratic. Okay, but this quadratic here cannot be factored, so I'm actually just going to multiply through by n here. Or it can be factored, but sorry, but we have 60 here, not 0, so we can't factor and solve. Instead, I multiply through. I'm going to move the 60 over. I have 0 there. Now it's not quadratic, it's a cubic. This is not something we do in the course. We don't solve cubics. There's a process to it, but we're not going to learn it. However, you can use on your calculator, use the apps button, go to the poly simulation number 2 that we've used before, and you can use that app to help you solve polynomials. If you're not sure how to do that, don't worry. We can do that in class, but the answer is 5 here. Okay, so I've shown you lots of examples, and yes, you've tried things, but I've also been supporting you through. Now it's time for you to just work solo. So I have a few more problems left. I will give very little guidance, and if you're done, just finish it off. You've been doing a lot of thinking already. If you want to try a couple more things and see how you do, excellent. Hang in there. I'm going to give you some more problems, and I'm just going to leave you wide open and see how you can do it. Let's try. Here's the first one. Read that, see if you can do it. And now you can check your work on that. I will not explain these ones. It's just going to be kind of quick. So I'll just say a couple words maybe. In this one, we know it has 4 terms. And because it shows them here, if it has 4 terms, then n must be 3. okay, like this. That becomes something like this when you expand it. We are given the first term, and we can set equal to that. By knowing the first term and knowing this here, we can solve for things. So this allows me to solve for a. Once you know a, you can then put it into another term. Let's say here I did the second term. I know the a value, and now that allows me to solve for b. That's a tough problem. Maybe you tried it, maybe you succeeded, but now as you look at it, check it out. Really good problem, but also really challenging. Okay, here's another one. These ones are a little different, so I'll get you started on this one. It says use the binomial theorem to estimate the value of this. Of course, we can punch that on our calculator and we'll quickly get an answer. But now we're going to use binomial theorem to estimate that. So here's how you begin this one. You say that can be written as a binomial like this. This is actually a binomial. And now that you have a binomial with the fourth power, you can use binomial expansion. Expand this fully and see, and then get the answer. That answer will be your estimate of that. So check your work here. That's a lot of stuff. There's the expansion. All the decimals, and you get an answer at the end of this. All right, and you're thinking, why do all that when I can just simply do this on the calculator in the first place? Well, there's a reason for it, and this ties to probability, and it's kind of one of the main reasons we also learn binomial theorem, but I'll show you that a little bit later. Okay, so try the same process on this one. Okay, and now check your work on that one. Okay, so I hope you tried expanding this and expanding this, and you may have noticed something interesting, and that is that this one and this one, they expand to the same thing, except one is written backwards and one is written forwards, right? So like the first term in this one is actually the same as the last term in this one. And the second term in this one is equal to the second last term in this one. So kind of backwards and forwards versions of each other, and that comes from the fact that these are reversed here. All right, so now the question is, will that always be true? Like if you look at this one, it's the same thing. They reverse the things. It's the same idea as this one. If you have two things where you reverse the binomials here, will they produce the same expansion? Okay, so the answer to that, okay, first of all, there's all that work. So again, that expands to this, and that expands to this. Of course, this has been rewritten in the backwards order, so it matches. All right. Or this one has. Okay, but no, it will not always work. If the exponent was odd, if you tried an odd exponent, you would notice it doesn't work out that way because of the negative signs and so on. There's different things that end up being positive, negative versions of each other. So it doesn't quite work. It's close, but not quite. All right, last one. This one is like the ultimate challenge. I think this one is extremely challenging. Maybe give it a try. You're trying to show that all of this equals 2 to the power n. Okay, so this is not even about binomial expansion anymore. This is just about these combinations. If you combine all those, will they be this? Give it a try. Okay, 2 to the n, first of all, can be rewritten as 1 plus 1 to the n power. So this is kind of similar to those ones we were doing a moment ago with the decimals. This might be a big leap in this one. Okay, well, let's try that now. So that we can expand like this. All right, the expansion of this is this. N power, 0 power, n minus 1, 1, etc. Okay? Now you can cancel a bunch of things. Bunch of things in here are equal to 1. Cancel all the things that are equal to 1. Okay. So that's actually 1, that's 1, this. All these things, 1 to any power is 1, 1 to any power is 1. Cancel all those. So you're left with those all added is what 1 plus 1 to the n is. But wait, we've shown that 1 plus 1 to the n power must equal to the n power then, because we showed that 1 plus 1 to the n power is equal to all these, the sum of all those combinations, and that's what we're supposed to show, that 2 to the power n is equal to all those combinations. So we've done it. Excellent. We've proven it. Tough one. Definitely lots of out-of-the-box thinking, and that is it. I think you are done thinking about binomial theorem for now. See you soon.